Hi everyone. Those of you who have been tuning in over the past 2 days might remember, my name is Park Ranger Joel Kane. And for those of you who tuned in over the past 2 days, or for those of you tuning in for the first time today, welcome to the virtual Grand Canyon GeoFest 2020, celebrating Earth Science Week. Yesterday's talks were all about rocks. Grand Canyon's three big sets of rocks, the Vishnu Basement rocks, the Grand Canyon Supergroup, and the layered Paleozoic rocks. And those talks yesterday about rocks will probably help us understand what we're talking about today. Today's talks are all about unconformities, missing time between various rock layers. And I am standing near one of the most famous unconformities in the entire world, the Great Unconformity in Grand Canyon, where the Paleozoic Tapete Sandstone is sitting directly on the Vishnu Basement rocks, creating a gap in time of over 1 billion years. That is a pretty incredible unconformity, and it's very well exposed everywhere in Grand Canyon. I'm standing at a really excellent exposure of it here below Indian Garden, not too far off the Bright Angel Trail. Now, you look at this unconformity right here, this incredible Great Unconformity, and there's one thing I want to point out about it. The Vishnu Basement rocks on the underside of the unconformity look a little strange here. They're kind of weird looking, they're kind of weathered, they're not really black like a lot of basement rocks, deeper down in the canyon are. And that's because of an interesting feature that you see a lot of places along the Great Unconformity, where Tapete Sandstone is sitting on the Vishnu Basement. And what we have to remember is that unconformities, as we'll learn over the course of the talks here today, are erosion surfaces. They are surfaces where rock was exposed at the surface to the elements, sometimes for very long periods of time. And when you expose rocks at the surface to the elements, to rain and wind, they start to alter. They start to break down and form soil. And of course, in order to form soil, you also need biological components. Soil is not just dirt, it's not just crumbled up rock, there's organic matter in soil. So soil starts to form at the top of rock surfaces that have been exposed to the elements for long periods of time. The surface of the Vishnu Basement rocks at the very top was exposed for a long time, and the top of it actually began to form a soil a very long time ago. Over 500 million years ago, as a matter of fact. The top of the Vishnu Basement rocks was actually turning into a soil, which is a lot weaker, a lot more crumbly than the actual Vishnu rocks themselves, which are pretty tough and strong. So at the top of the Vishnu, along this Great Unconformity, oftentimes you'll see this, where the Tapete Sandstone is actually tougher and stronger than the basement rocks underneath. And as the top of the Vishnu is eroding back, the Tapete is actually sticking out a bit on the very top. That's the unconformity right there. That's the time gap of 1 billion years. I could walk over there and actually literally put my finger right on that unconformity, which is pretty incredible to me. Now, our first talk today is going to be focusing on the Grand Canyon Supergroup. We talked a lot about that yesterday, the two groups of the Grand Canyon Supergroup, the Unkar and Chuar groups. This talk is going to explain exactly why we only see them in very specific areas in the canyon. It actually has a lot to do with erosion surfaces, unconformities, and missing time. So I hope you enjoy that first talk, and then the talks after that are going to be delving even more into Grand Canyon's unconformities, including the most famous, the Great Unconformity. So thanks for joining us here today.
Well, hello again, everybody, and welcome to the second day of talks here in Grand Canyon Geology Festival, or GeoFest 2020. And today's talks are all about time and missing time and unconformities, gaps in the rock record, and here talking with us today about some of those gaps, why certain rocks in the canyon only appear in certain places, which can be really confusing, is Wayne Ranney, who he likes to say in the mid-1970s wandered into Grand Canyon and never came out. He worked as a backcountry ranger here at Grand Canyon National Park, and finished his geology degree at Northern Arizona University. And after that became a river guide on the Colorado and San Juan rivers. Received an advanced degree in geology and began working as a geologic interpreter around the world. So he's now a geologic educator, an award-winning author, and lecturer on outdoor adventures and worldwide expeditions. His geology-themed river trips and hikes in the Grand Canyon in the Southwest are very popular. He's written several books which are incredibly useful for understanding the geology of Grand Canyon. I recommend them to folks all the time, but they are still quite accessible to general audiences as well. You don't have to be a geologist to read them. So with that, welcome Wayne Ranney. Thank you very much for being here with us today.
Well, thank you very much, Ranger Joel, for that wonderful introduction. I'm very happy to be a part of GeoFest 2020 at Grand Canyon National Park. And I've been looking at the geology of Grand Canyon for 45 years, and I never get tired of it, and I love it. And this evening, what I'm going to share with you is try to help people understand a little bit better this unique character of Grand Canyon's supergroup rocks. They're not found everywhere in the Grand Canyon, and that's very confusing to people. So I thought what I would do is just try to, as much as possible in 15 minutes, make this idea a little bit easier for people to understand. And we'll jump right into the slides here for the supergroup. And I've called this lecture Making Sense of the Supergroup. And I hopefully will be able to understand the supergroup just a little bit better after this talk. The goals of this talk, as I've stated before, is to help people such as yourself who may be interested in Grand Canyon's geology, to better understand the seemingly random outcrop pattern of the supergroup and describe in plain terms how its discontinuous and often confusing exposures were formed. You know, why is the supergroup here but not there? Why do we see it over here but not there? And this is the typical postcard view of the Grand Canyon, a couple of features labeled there just to show you what we're looking at from Grand Canyon's South Rim. And you can see this patch of the supergroup rocks that are located just below Cheops Pyramid. And most people look down into the Grand Canyon and they never notice that there's this wedge-shaped block of rocks. But for people who are at the Grand Canyon a little bit longer than a few hours, they might hear a ranger talk or hear a guide talk about this. If we go down the Kaibab Trail just a little bit, we can see this same outcrop. This is down in the Redwall limestone, and there's that little patch of the supergroup that you see there. But you look across the Colorado River to the south, and the supergroup very, very close to this outcrop is not there. And so this can be confusing. And a lot of times when you're on the river, you'll come around the corner and you'll see these beautiful outcrops of the supergroup. And there I've highlighted it for you in this color. Every other rock you see there is not part of the supergroup. And it looks like this wedge-shaped block of rock is just floating in space there. And I can understand why non-geologists might think that the supergroup is really mysterious, because it just, your guide will tell you, oh, there's the supergroup, and it's not behind us and it's not ahead of us. So just to review, these are Grand Canyon's 3 sets of rocks, and I love this diagram because it's beautifully colored and it highlights the 3 main packages of rocks. And 4/5 of Grand Canyon walls are made up of what are tinted in this diagram blue Paleozoic strata. And they're flat-lying generally, and they make up most of the walls of the Grand Canyon. And then down at the very bottom, colored in this light green, are the Vishnu schist and Zoroaster granite, which we call the basement rocks. This is the foundation upon which all of Grand Canyon's other rocks have come to rest. And then there we see the supergroup colored in orange. And Every time it's depicted in one of these diagrams, we see it at an angle, and we see it sort of pushed or shoved into on top of the Vishnu schist and underneath the Paleozoic rocks. And I can readily admit that this can be confusing to people who are first trying to understand the geology of the Grand Canyon. But I think we'll be able to unravel that for you here in the next few minutes. So first of all, why the name supergroup? A lot of times people make a joke that is this some famous rock band that it was named after or something? And it's not that. Geologists have a classification scheme for rocks, and the very basic classification is the rock formation. And a formation is a laterally continuous body of rock that's different from what's above and below it. And formations can be subdivided into members. And in the Grand Canyon, the Red Wall limestone has some members. The Muav limestone has members. Even the Kaibab formation has members. And occasionally there'll be a very specific bed that can be readily identified, and that's called a bed. But if we go in the other direction of classification, sometimes formations can be brought together into what is called a group. And these group of rocks either share a very common depositional environment, or maybe they were deposited very closely spaced in time. And in the Grand Canyon, we have some groups. We have the Tonto group, we have the Supai group, and then we also have the Unkar and Shuar groups, which together, those two groups then become the Grand Canyon supergroup. So this is where this terminology comes from. It's just a way to classify rocks. And the Grand Canyon supergroup, for many people, is very difficult to understand because of its discontinuous nature. And believe it or not, it's over 12,000 feet thick, 2.5 miles of sediment. And it's discontinuous in its outcrop and its preservation. We don't see it everywhere in the Grand Canyon. It's generally always tilted down towards the northeast, and this is an important part of why it's present only in a few places. Is composed of 8 different rock formations, and as I said, they're in 2 different groups. And fortunately, the supergroup has relatives or other groups of rock nearby that help us understand how it got into this discontinuous pattern. So when we think of this being over 12,000 feet thick, 2.5 miles of sediment, you can see the hikers down there just being overwhelmed in these supergroup rocks hiking in Mineral Canyon. Here's a cross-section of the supergroup, and the 12,000 feet equal 2.5 times the modern depth of the Grand Canyon. So over there on the right, I've taken that previous cross-section of Grand Canyon rocks, and I've got 2.5 of them stacked one on top of the other for the entire thickness of the supergroup. Hiking out from one Grand Canyon is hard enough. Imagine hiking out 2.5 Grand Canyons. That would really be something. And a lot of times people ask, how can the supergroup be over 12,000 feet thick when the Grand Canyon itself is only 5,000 feet deep? And the answer is because it's tilted. And if you look at this diagram of the Shuar group, a geologist will take a measuring stick and measure the thickness of rock perpendicular to its bedding, and then walk down that same bed back to the creek, and then they measure up again to the next noticeable bed. And just through this tilted section of rock, you can see how over 2.5 miles of sediment can fit into a canyon that's only a mile deep. So this is how we do it. Because it's tilted, we can get 12,000 feet. Most places in the Grand Canyon have no supergroup, and as you see this right here, this is where the Tapete sandstone sits right on top of the Vishnu schist. And as we've learned from other lectures in this series, this is called the Great Unconformity. And where you see that yellow line, there used to be 12,000 feet of supergroup, but as we're going to learn, it became eroded away. So this is a map that shows the outcrops of the Unkar group, and there's about 6 major outcrops of it. I'll just label them for you: Tapete's Creek, Shinnemoo Creek, Crystal Creek, Bright Angel Creek, Clear Creek, and the area around Hance and Tanner. And those dark areas that you see there are the outcrops of the Unkar group. The Chuar group is even more restricted, and it's just in these yellowish areas in the lower part of Marble Canyon and the upper part of the Grand Canyon, just adjacent to where the Little Colorado River comes in. So these are the only places where these rocks can be seen. And this is the meat of this little talk right here. This is an illustrated history for how the supergroup got to be in these tilted wedges only in a certain part of the Grand Canyon. And it starts out with the very important idea that regionally across the Grand Canyon region, the supergroup was deposited as flat-lying or horizontal sedimentary rocks. And here in this diagram, we can see where the supergroup was laid down over about a 500 million year period and buried the eroded remnants of the Vishnu Mountains. So it's very important to realize that the supergroup was once everywhere throughout the Grand Canyon region, and it was deposited horizontally. And there's a close-up view of one of those supergroup rocks just sit there artistically on top of the Vishnu schist and the basement rocks. Now, about the relatives that it has, there we can see in this map of the southwestern United States where the supergroup crops out. But in the Death Valley area, there's another package of rocks called the Pahrump group, and a part of these rocks are the same age as the Unkar group. Down in central Arizona, we have the Apache group. This may be the closest relative that we have to Grand Canyon supergroup. And then up north, we have the Uinta Mountain group. And if we just remove the photographs there, you can see that region-wide throughout the Southwest here, there are correlative rocks that relate to the supergroup and tell us that this was a period of deposition of sedimentary rock in the American Southwest. So this tilting that occurs in the supergroup rocks began when there was a rifting event and the blocks of the supergroup began to become tilted, generally about 15 degrees down to the northeast. And this is where this regional tilt was imparted on these rocks. And you can see those once flat-lying rocks now at an angle of about 15 degrees. And this is a photograph from Red Canyon along the Hance Trail. And that is the original angle, the angle that you see today inside the supergroup. Now, the important thing is that some of these blocks during tilting were uplifted and others became downdropped. And those thick yellow lines in the diagram are two great big faults where these blocks of rock have been moved differentially to what's adjacent to them. And the blocks that were uplifted the highest are the ones that experience the most erosion. So watch the diagram closely and you'll see erosion begin to wear down on these rocks. This is a photograph from the Utah Flats area. I took this photograph from the South Kaibab Trail, and you can see this block looking across to Utah Flats. Even though that down drop block with the downward pointing arrow, it stands high in the landscape today, but that's because it was downfaulted, just like the cartoon above it. So the higher blocks became completely eroded away, and there they are eroding away. Erosion also attacked the downfaulted blocks, but erosion proceeded in such a way that only the blocks that were faulted the lowest became preserved. And on the right and left of this block right there were supergroup rocks, but they were completely eroded away. And if we go back to this diagram, we can see where the supergroup was uplifted, but completely eroded on both sides. And in the middle is the low faulted block that was preserved. Very interesting the way that works. I know this can be confusing because a lot of times these blocks that were faulted low in the ancient landscape, they were faulted so low that they escaped erosion. Had erosion commenced for another 50 or 100 million years, all of the supergroup would have been eroded away and we would never have a record of it. but fortunately some blocks did survive. And they were later buried by the sedimentary rocks of the Paleozoic era, and you can see that wedge-shaped block that's captured down there, and later the Grand Canyon is going to be carved there. Now there is a little bit of a rhyme and a reason to the supergroup blocks, and here's this dragon map, or the geologic map of the eastern portion of Grand Canyon. And if we zoom into the areas where the supergroup can be found, these very warm colors that you see are where these tilted blocks of supergroup can be found. And I'm drawing these dark lines in there. And these are probably related blocks that are connected to one another in the subsurface. And there's even a very tiny one right there in the upper parts of Shinnemoo Creek. There's a little bit of Shinnemoo quartzite that crops out in the upper part of Shinnemoo Creek. And you can see that these tilted blocks are running to the northwest, and they're tilted down to the northeast. And the rifting along the continent at this time is probably what caused these blocks to become tilted. And here's a paleogeographic map during the Cambrian time period, Tapete Sandstone, Bright Angel, and Muov time. And those blocks are shown here as islands that were sitting in the Cambrian Sea, because these low faulted blocks were standing high in the sea, and they became buried by Cambrian age rocks. So this is a photograph from down along on the Hance Trail, and we're looking across towards Wotan's Throne. And you can see where the tilted supergroup block is right here. And then watch how the Tapete Sandstone comes in and gets washed up against this preserved highland right there. These are spectacular examples of paleogeography. And you can almost imagine standing on that tilted group of rocks that belong to the supergroup and watch the Tapete Sea washing all around just below the top of the cliff. So just in summary here, if we look and see the history of the Grand Canyon for this time, from 1300 to about 1250 million years ago, the Vishnu Mountains had been completely eroded down. There was a little bit of a surface that was developed there. In many parts of the Grand Canyon, this is where the great unconformity is going to form. But before we get to that part, we have to deposit the Grand Canyon supergroup. And between 1250 and about 740 million years, there was region-wide deposition of the supergroup, both the Unkar group and the Chuar group. And these sedimentary rocks, 2.5 miles thick, were then subjected to faulting and tilting and partial erosion. And the blocks that were faulted the highest were eroded completely away. And only the blocks that were faulted very low in that ancient landscape escaped this ancient erosion interval. And down here at the bottom of this diagram, you can see 2 tilted blocks of supergroup that are buried by younger strata. And they're going to be preserved into the present day. And the present day gives us this kind of a cross-section where we can see the Grand Canyon has been cut mostly through Paleozoic rocks, but in the very bottom exposes the Vishnu basement and a few blocks of the Grand Canyon supergroup. The Grand Canyon staircase is composed of much younger rocks that used to sit on top of the Grand Canyon. And it's very likely that supergroup rocks exist under the area around Lake Powell, where there's been some drilling for oil, and they have encountered Precambrian sediments that appear to be related to the Grand Canyon supergroup, but many, many millions of years away from being exposed to us. So these are the 3 sets of rocks that are in the Grand Canyon. Hopefully this will clear up some things for you about why we find the supergroup in these tilted, isolated patches. They've had a wondrous history, and thank goodness the erosion back over 1 billion years ago did not take away the supergroup entirely. And I hope this helps everybody that's watching, Joel, and I'd be happy to talk a little bit more about the supergroup if you think that's in order now. Thank you.
All right. Well, thank you very much for that, Wayne. Those animations are spectacular. They're really, I think, really helpful for understanding exactly like how that happened and how things got to be the way they are now. It's easy to talk about things that in kind of in the abstract, but having like an animation like that to actually kind of show it in a way, I think is really helpful. So yes, thanks for
Well,
those.
thank you for that. I spent a lot of time on those, trying to get them to be informative for people.
Yeah. Um, no, awesome. Yeah. And I remember the first time I ever hiked down South Kaibab Trail, and I got down, down through the Tapeats below Tip-Off, and first time I ever actually got down into supergroup layers, and I was really excited about it. And something I was looking out for on that hike, and that I found, and I was ecstatic when I found it, was you were talking about islands, islands of supergroups sticking out of the Tapeats Sea, with the Tapeats sands kind of onlapping these islands. And you had these big cliffs, these huge cliffs of Shinemu sticking up out of the sea. And there's places, and I think you write about this, I think in your book, big chunks or cobbles of Shinemu that broke off from these cliffs and landed in the sands down below and got encased in the Tapeats sandstone. And the first time I saw that, I took like a million pictures of it, and it was really exciting. So that's one of my favorite things.
I agree with you. That is one of my favorite
canyon.
things too, along the South Kaibab Trail, just below the Tip-Off. You can actually see blocks of the supergroup that fell off the still existing cliff, and they just got washed over with loose sand, which is now the Tapeats sandstone.
Yeah. Yeah, of course, you talked about the great unconformity, and Dr. Carl Karlstrom, who's up next here today, is going to be delving more deeply into the great unconformity and what exactly it is. So stick around, if you want to learn more about that. But I loved some of your pictures along the New Hants Trail, because I got down there finally. It had been a trail I wanted to hike for a long time, and I finally got down there last fall. And that's actually, the picture behind me is down here in Hants Rapid. Now, I didn't take this one. I took a bunch down here, but I was down here a little later in the afternoon, and the lighting wasn't quite as good as this here. So, but yesterday, of course, we talked a little bit about the supergroup with Dr. Michael Timmons and Dr. Carol Deller about the Unkar and Chouar groups. And Dr. Timmons, we were talking a little bit about this area here too as well. And I think I mentioned this huge dike cutting through the Hackattai Shale right here that I sat and stared at for a while and took a bunch of pictures of. So the supergroup rocks they're cool. They're really awesome. Unfortunately, I've not yet had the opportunity to actually get up close and personal with any of the Chouar group.
Yeah, well, when you get to do a river trip, I think you'll be able to see the Chouar group. That's the best way to do it. And there's a wonderful loop hike that will take you back into the Chouar group. And I think, as Dr. Deller might have shared with viewers yesterday, the Chouar group is a really unique package of rocks that we don't have too many rocks of that age on planet Earth. So it's kind of wonderful here in the Grand Canyon that specific period of time, generally around 750 million years ago, is not well recorded on planet Earth. But Grand Canyon has a package of rocks from them, and fortuitously, they're preserved over there in the eastern part of the canyon.
Yeah. Just one more awesome thing about Grand Canyon. There's a lot here.
Yes, there is. And I have to tell you, Joel, I don't envy you in a ranger talk or a ranger walk, even having to bring up the supergroup. I've done 5-day backpacks that are geology themed where I don't mention the supergroup because it's just something that's a little bit more advanced to try to understand these isolated wedges of rock. And if, I don't envy you having to do that, but
yeah. there's a lot of rangers here who don't have, geology backgrounds who really don't like to talk about the supergroup, and they generally avoid it. And I don't even talk about it all that often. I do sometimes. There's one talk that I do that I very much go into detail with the supergroup. But I was saying earlier, that concept of having islands sticking up out of the sea and boulders falling down into the sands around them. One of my favorite things in the canyon, I hardly ever talk about that, because you have to cover a lot of ground in order to get to that point where you can talk about that.
Well, I'll tell you one little trick that I've learned if I mistakenly mention the supergroup and I find myself really in deep water, so to speak. I will tell people as we're going down the trail, looking at the Grand Canyon, imagine sea level rising up and filling the Grand Canyon. And of course, I have to mention that's virtually impossible. The Grand Canyon's too deep, too far away from the sea. But just for an exercise, imagine the Grand Canyon filling with water. And then also imagine that the seawater is leaving behind flat-lying sand. So everything that's open space, like behind you right now in that view of the Grand Canyon, gets filled with flat-lying sediment. Then imagine if a river comes down out of the north and flows to the south and cuts a new Grand Canyon. What you're going to see is that flat-lying sediment that's filling in the Grand Canyon, and then all of the rocks that sediment was deposited on. And that's sort of a modern, future-looking view of filling in a space around irregular topography. And I've used that to some good effect if people want to understand the supergroup filling in pre-existing geography.
Yeah. And one thing, of course, I love about the supergroup is we were talking a little bit about this yesterday, is how it tells us about, kind of the birth and death of a supercontinent.
Yeah.
And again, we had talked about this a little bit before, but so lots of people are familiar with, with Pangaea, the last supercontinent that existed on the planet, and the one we know the most about. But there were supercontinents before that. Not as many people have heard of Rodinia.
Yeah.
And of course, the supergroup, tells us some things about that, which a supercontinent, over 1 billion years old. That's a pretty cool thing.
Well, I just want to thank you guys for putting this series together. I think it's wonderful for visitors and supporters of Grand Canyon. And thanks to Dr. Carl Karlstrom at University of New Mexico for organizing it. And I'm very happy to contribute, and I hope people get a lot out of this.
So do I. Yeah, so do I. And maybe hopefully some folks will have some questions for us after this, or that we can all help answer. Part of the hope is, having these talks down recorded will provide a resource for people,
Yes.
Who want to learn more. And also even for rangers here at the Canyon, we'll definitely be referring to these for, to try and help interpret the geology of the park for, especially folks who don't have that background in geology.
Well, Joe, I'm very happy to share my animations with you because I know you'll use them.
Oh, wow. I'd be honored to have those. Yeah, because those are really cool and I think really helpful. So, all right.
All right. Well, I'll check out. Thanks, everybody, for watching. Bye-bye.
Thanks very much.
For Green Canyon.
Hello again, everyone. So today we're talking about unconformities, gaps in the geologic record, pieces of missing time between rock layers. And that first talk, of course, was focused on the Grand Canyon supergroup and why we only see it in a few places within Grand Canyon. There are unconformities between the supergroup and the underlying basement rocks, and between the supergroup and the overlying Paleozoic rocks. And as we mentioned earlier, of course, anywhere where the Paleozoic rocks are sitting directly on the Vishnu basement rocks with no supergroup at all, then that is known as the Great Unconformity. But as our next talk will hopefully make clear, the Great Unconformity is actually made up of a number of smaller unconformities, as that last talk alluded to. And there are actually unconformities between a lot of the different rock layers you see out here in Grand Canyon. Some of them hundreds of millions of years, some of them just a few million years, like the one back behind me here. I'm standing directly beneath a really spectacular contact between this brick red, soft, crumbly Hermit shale and the overlying strong, tough, well-cemented, pure quartz Coconino sandstone. And this beautiful contact is exposed right along the Bright Angel Trail. Now, if you look up at that contact, you'll actually notice, hopefully, that the Hermit shale is eroding back underneath the overlying Coconino sandstone because it's so much more soft and crumbly than the overlying sandstone is. It erodes back and the sandstone forms overhanging ledges, which over time, well, gravity doesn't really like that, so they break and collapse as giant landslides periodically. And that's a very common erosional pattern you see here in Grand Canyon, where stronger, harder, tougher rocks are sitting on softer, weaker, more crumbly rocks. They erode back, the overlying layers collapse as landslide blocks. Hence all the boulders on the slope back behind me here of Coconino sandstone. Now, one thing I want you to really try to remember about unconformities, they're kind of confusing. They're erosional surfaces. They represent periods of time where new rocks were not being deposited or when rocks were actively being eroded away. Now, a lot of folks will look at a contact like this. It's almost a perfectly horizontal line between two different rock layers. And they'll ask, well, how is that possible? How can it be so flat? Well, first of all, it's not always perfectly flat. Sometimes there's actually preserved paleo or ancient topography along those contacts, small hills and river channels, but other times it is extremely flat. But to understand why that is, you have to remember how erosion works. Rivers and streams are flowing down to the ocean. They are eroding things down to sea level, which is a flat surface. So, especially with rocks like these, which were forming along a coastline, rivers and streams are eroding these rocks away down to the ocean and forming a very flat surface. So that's why these contacts, like this one between the Hermit and the Coconino, look the way they do. And I hope you stick around for our next talk here. It's going to be really awesome, discussing the great unconformities, plural, of Grand Canyon. Thanks for joining us.
All right. Well, hello, everyone. We're here today with Dr. Carl Karlstrom, who is a distinguished professor at the University of New Mexico. His research is in structural geology, tectonics, and landscape evolution. And he grew up in Flagstaff, Arizona, started his Grand Canyon research as a professor at Northern Arizona University, and then has continued that research at the University of New Mexico since 1991. He initiated and installed the Trail of Time expedition here at Grand Canyon National Park with grants from the National Science Foundation. And his Grand Canyon-related science research grants from the National Science Foundation total more than $1.5 million over 30 years. And his contributions to the body of research on Grand Canyon include more than 65 journal articles, 2 geologic maps, 130 abstracts at professional meetings, and the completion of 4 PhDs, 10 master's theses, and many undergraduate research theses on Grand Canyon topics. So, Dr. Karlstrom, thank you very much for being here today.
Yeah, it's great to be here. The title of this talk will be Grand Canyon's Great Unconformities, plural, with up to 1.3 billion years of the rock record missing in Grand Canyon. That's almost a quarter of Earth history. So, geologists have to wear a lot of hats, and this particular hat is, for this talk, involves missing time. So I'm talking about nothing in a way. So I'll take off the hat, no hat for today. But I want to give you a little summary as of 2020 about some of the main ideas about the unconformities in Grand Canyon and some new research that's going on, exciting new research on this topic. And I hope to kind of hit all learning levels and as well as the hottest research. So let's see if we can. So what's an unconformity? An unconformity is basically an erosion surface that's trapped in the rock record. There's 3 different kinds. I'm just going to kind of breeze through them so you've heard the term. A nonconformity, that's kind of my favorite one, is when a mountain range is beveled by erosion down to a flat surface. And that's and then the next layers of sediment that get deposited on this surface is, I'm going to annotate here. Oh, spotlight. So this surface here be something like the continent of Australia. If you started depositing layers of sediment on top of that, you'd have sedimentary rocks, sed layers, on unroofed igneous and metamorphic rocks that were once part of a big mountain range like this. That's a nonconformity. An angular unconformity is when a bunch of layers get laid down and then they get tilted. That's interesting structurally too. Layers are horizontal and then tilted, and then beveled, and then new layers on top. So you have this sedimentary layers are deposited on other tilted sedimentary layers. And then a disconformity is when you have a bunch of layers deposited, then a break, time erosion, and then more layers deposited. So those are the 3 types: nonconformity, angular unconformity, and disconformity. We'll just look at them in particular there. Now, if we go to Grand Canyon, John Wesley Powell noticed in his early trips that there were 3 basic sets of rocks separated by these magnificent erosion surfaces or unconformities. So we have the layered Paleozoic rocks on top, this flat-lying erosion contact, which is, as you can see, an angular unconformity, and then this lower unconformity where the middle set of rocks, the Grand Canyon supergroup, was deposited on the Vishnu basement. Powell, or his artist, one of the 2, drew this wrong, so we've redrawn it over here. And the reason it's wrong is that lower contact can't be right, can it? The layers had to be deposited flat on this unroofed basement before the whole package was tilted, so that this non-conformity down here in white has to be tilted like the sedimentary layers above. And then all of that was beveled along this, what I call the great angular unconformity, and then the flat-lying rocks. And there's some nice disconformities up here in the flat-lying Paleozoic rocks as well. So Grand Canyon has it all, as is true for so many aspects of geology. So I want to introduce these terms. There's a lot of confusion. It's some difficult concepts, but bear with me. I'm going to use this term, the great nonconformity, for the place where the Grand Canyon supergroup sits on unroofed basement. The demise of a mountain range is represented by that white line. Amazing concept. And then I'm going to use the great angular unconformity for the places where the flat-lying rocks are on top of the tilted Grand Canyon supergroup. And look over here to the left, what happens when the 2 come together. Sometimes, in many places actually, most places, the flat-lying sedimentary rocks are sitting on basement, and that's what Powell term he used the term great unconformity for. So let's look at it in person here. Here's the Vishnu basement rocks, the great nonconformity, the unroofed basement, flat-lying. They were initially flat-lying Grand Canyon supergroup, then those got tilted, and then here's the flat-lying rocks above. And yes, there's some disconformities like up at the base of the red wall up in here. So we can see them all in one place. This happens to be a view from near Horseshoe Mesa. There's Sockdolager Rapid down in the right. Okay, I hope you're getting the concepts, but you can go anywhere on Western North America and see also great unconformity. So this concept here is that this is a regional, if not a global event. That is, this is in Ouray, Colorado. Here's 1.75 billion-year-old basement, same age as Grand Canyon. Oops, sorry. And overlain in this case by Devonian rocks. So here there's 400 million year Devonian base sediments on 1.75 billion year old basement. So there's 1.35 billion years missing right at that contact. I think you're getting the idea that we know the age of the rocks above, often we know the rocks of the age of the rocks below. And so the amount of time missing is the difference between those two. And the new research we're doing is trying to figure out what's happening during that missing time. Here's what it looks like from my home in Albuquerque, the Sandia granite underneath, 1.45, the Madera limestone on top, 300 million, so they're a little over 1 billion years missing. And if you go to the famous angular unconformity in Scotland, Hutton's Sicker Point angular unconformity, you can see the old red sandstone deposited relatively flat across these tipped Silurian rocks. Here there's only like, 60 million years missing, but a lot can happen in 60 million years. And these unconformities, even since Hutton's time, have been sort of a hallmark of major events that are recorded in the rock record. Not, and so the amount of time at that unconformity is important to figure out, both in terms of what happened to the rocks below and then what's the setting for the new rocks above. Powell knew about Hutton's unconformity, in fact, and he thought that the Unkar group was this old red sandstone because he saw this nonconformity in Grand Canyon. So there was exchange of ideas from Europe to the US even in the 1800s. Okay, so here's the same thing, a little more detailed. 3 sets of rocks, flat-lying rocks, tilted rocks, and the basement. And these terms that I'd like to kind of introduce: the great nonconformity, where you unroof the basement rocks; the great angular unconformity, where the tapetes, the flat-lying rocks, bevel across the tilted supergroup, and where the two come together, in other words, where there isn't any of this Unkar group preserved, we have this great unconformity, which is what you see in lots of places in Grand Canyon. This is kind of, I call it the money diagram. This is the one if you want to, I don't know, carry one in your pocket when you're hiking in Grand Canyon, just so you remind yourself about time and rock. This is a rock column here, and you can see the 3 sets of rocks, and then this is the time column over here. All the black is time missing. Now the time's not missing, the time went by, right? But we just don't have a record of it. So here's the basement down here. Here's the Unkar group in purple, the Chuar group in orange. Here comes the layered Paleozoic rocks, starting with the Tonto group. And even up here in this section, looks so complete, there's lots of time missing. And so I've tried to encode the amount of time missing. But here at the great unconformity where the Tapetes sits on the Vishnu basement, again, up to about 1.3 billion years of time missing. GA means giga-annum, is like a gigabyte, a billion years. So, okay, so that's kind of a nice visual. And to give you this idea that in spite of the fact Grand Canyon is one of the best geologic records in the world, there's as much time or more time missing than is recorded. And that's true of every place on Earth. Okay, so if we look at why is this unconformity in some places and not in others, that is the great nonconformity, it's because the supergroup, the tilted rocks, is only exposed in some places. So these black outcrops are the Shinemu sandstone of the Unkar group that are in these fault blocks, and they're only preserved there. That is the great nonconformity, and the presence of the Grand Canyon supergroup is only exposed in these northwest trending fault blocks that end up forming some interesting topography at the time of the Cambrian advance of the seas. So these are signs from the Trail of Time exhibit. Kind of break it down a little bit. Again, this concept, you had to erode away these Vishnu mountains. You had to get rid of 20 kilometers of crust. We know that from the metamorphic information down here in the preserved rocks. So we eroded that much material. We had a flat surface, and then we deposited the Grand Canyon supergroup. Then we tilted that, and then we beveled that. So this is a kind of, this picture on the right shows again this concept of multiple erosion surfaces that represent huge amounts of time separated, that separate the basinal stages, let's say. Another sign, the same thing. Of course, this is a little more detail. Here's the Unkar group deposited in fault blocks. They got tilted. The Chuar Seaway advanced across. And so this idea that there was erosion surfaces recorded several times in the geologic history of the Grand Canyon rocks. And you can go see these up close and personal. If you walk up the North Kaibab Trail from Phantom Ranch towards the North Rim, this is the great nonconformity where the Vishnu schist. These rocks came from 20 kilometers deep in a now eroded mountain range. Here's the evidence, the erosion of that mountain range, because these rocks, the Hautoda conglomerate member of the Bass limestone, they were deposited near sea level. So here's the erosion surface, and here come the first gravels deposited on this weathered surface. If you go into Blacktail Canyon on a river trip, you can see again the unroofed Vishnu basement rocks, but here there's no Grand Canyon supergroup. This is the Tapeats sandstone with cross-bedding and little gravel layers and breccia layers that were deposited on a surface which had been unroofed initially by supergroup time, then beveled again before the advance of the Cambrian seas to deposit the Tapeats. If you want to see probably the best view of the Great Angular Unconformity, drive over to Lippin Point on the East Rim Drive, and you can see all these tilted layers. And Powell recognized this when he floated the river here in 1869, that this was a huge thickness of sedimentary layers. But since they're tilted, you never see them all stacked up in one place like you do for the layered Paleozoic rocks on top. But he nevertheless recommended that recognized that this thickness of Ankar group is much greater than the thickness of Paleozoic rocks. So you can see here's the Vishnu basement way off to the left, and then all the layers of the Ankar group, and then the beginning of the Chuar group also shown underneath this angular unconformity. If you go to Yavapai Geology Museum, you look out the beautiful window there, the room with a view, you see an island really of the Grand Canyon supergroup, the tilted rocks, sitting on top of the basement. So there's the great nonconformity, and lapped on against by the Tapeats sandstone. And this island, I'll show you another picture later, was sticking up into the Cambrian Seaway as the sands and muds advance from west to east across the erosion surface. So it's an erosion surface trapped in the rock record for us to get a glimpse of a major erosion period. If you walk down Bright Angel Trail, here's these rocks in the foreground are the Vishnu basement rocks, and here's the Tapeats sandstone. There's a hiker back there for scale. Here's the trail. So you get a really up close and personal view of the great unconformity there. If you walk out to Plateau Point, you get you feel like you're looking straight down into the river. Here's Horn Rapid down below. And I think everyone, their eye automatically picks out these things. And now I hope you can begin to sort out a little better what they are. That's obviously an unconformity, flat-lying Tapeats on top of basement. Here's Bass on top of basement. Here's Bright Angel on top of Shinemu. And so as you begin to sort out the views and learn about the time missing as well as the rocks, you see the great unconformity, you see the great nonconformity here. You see the angular unconformity where the Tapeats beveled across the tilted Shinemu. And you can see that the Shinemu island was sticking up a couple hundred meters above the sea as these sheet sands were deposited against it. So there's tremendous history to be seen across these unconformities in Grand Canyon. So sort of a new twist on the great unconformity research is that this unit in eastern Grand Canyon called the 60 Mile Formation, which we used to think was Precambrian. We've now redated it, and it turns out to be Cambrian. So rocks above are Cambrian. Rocks, they're about 508 above. Rocks below are Cambrian, about 530 below. And so now we know that there was an event that tilted Cambrian strata all during the Cambrian, and then that eroded surface was covered by flat-lying Tapeats. So the concept there's Cambrian tectonism that's recorded now in the Grand Canyon that we have to figure out what was causing that, what was driving that on a global scale. We think it was probably reactivation of the nearby Butte Fault, which caused the Cambrian sediments to be tilted, beveled, and unconformably overlain by the next layers. So just to put it in perspective, sorry for the lot of words, but there's some interesting global debates about the great unconformity. The term was first used by Dutton in 1882 in Grand Canyon. Same time it was being recognized in the Black Hills and in Colorado by G.K. Gilbert. More recently, people have thought of it as a single event, maybe the trigger for the explosion of life, of diversity of life in the Cambrian. That's this Peters and Gaines paper. Or maybe by a really deep erosion caused by ice before the Snowball Earth episode, Keller et al. Paper. Or maybe coinciding with a major oxygenation event, these ideas that it was a single event in Earth history. Other people have said, no, these are erosion periods related to the assembly and breakup of supercontinents, or maybe even to the onset of global plate tectonics. So these are all interesting papers that have proposed an event sort of approach for this regional or global erosion surface. My bottom line from working in the Grand Canyon is that it's not a single event, it's a composite erosion surface formed from several major periods of erosion, and probably was related to the assembly and the breakup of this supercontinent of Rodinia. So thanks for listening. That's from 101 geology to the present ongoing research, all involving lots of interesting questions and problems about these rock contacts. And I don't. I got to end with the summary slide, and I'll just finish there. Thanks for listening, and we can go to questions.
Well, thanks so much, Dr. Karlstrom. Time is actually one of my favorite concepts in geology, and of course, unconformities or gaps in the record are one of those things that tell us a lot about time. It's like to say, that the absence of data is also data. that we actually learn. We can learn things from the absence of something, which is kind of a funny concept, but it's true.
Yeah.
I got really excited there for a moment when you showed the picture from Ouray, Colorado.
Yeah.
Because I was just there like 2 months ago, and I stood in that spot and looked at that contact for the first time, just like about 2 months ago, and it's kind of amazing, working at Grand Canyon for years, and then going up there into Colorado and seeing basically the same great unconformity, essentially, just with slightly different strata,
Yep.
So yeah. The idea that it's not just in Grand Canyon, it's like it's a regional, or even a global feature that's been recognized.
So question for you, Joel. I mean, in interacting with the public and trying to help interpret the resource behind you, that Grand Canyon, what are the things that people get mixed up about? I mean, I know there's a lot of complicated concepts in there about unconformities, but which are the things that you have let's say the most success or the least success trying to help people see these contacts in the Grand Canyon?
Well, I guess one of the biggest things is just when you talk about missing time, that an unconformity represents time that's not there, and you talk about the great unconformity, you say there's over 1 billion years that is not recorded, at least in some places, where the Paleozoic rocks at least are sitting on basement. It's over 1 billion years missing, and a lot of people's first question is, well, where did it go? Where'd the time go? Was there just nothing happening for 1 billion years? why isn't it recorded? And then that brings you to start talking about the deposition of rocks is not continuous.
Right.
The deposition of sediments, forming layers of sedimentary rock, it's not something that's happening continuously all the time. So I'll try to talk about, we look around, the whole idea of the present is the key to the past. You look around on Earth today and you see, sediments are being deposited in certain places and not in others. And that was, that's been the same for all of Earth's history. Sometimes sediments are being deposited and other times there aren't. So, there might not have been rock deposited at all for a really long period of time, or maybe there was and then it got eroded away. So just trying to get folks to understand, well, the time is there, the time happened, and that there were things happening during that time. It's just that we might not have a record of them, in certain places.
Yeah, yeah. The preservation is the thing about rocks. I mean, lots can happen, but is it preserved in the record? And so, beauty of Grand Canyon, like you're saying, if you see where the Tapeats sits on the basement, you say, what happened during that 1.3 billion? And you can then just say, well, let's go to Lippin Point, and we'll look at the Grand Canyon supergroup. That fills in the gap a little bit. We can go along. We can say, okay, that package of rocks records part of this missing time, and that's
exactly.
And geologists can do that globally. We can say, okay, well, the record's not perfect in Grand Canyon. Let's go to China and see what's happening across that time interval. So this concept that the preservation, we have to piece together spotty preservation from outcrops all over the world for geologists to put together the time scale. It's pretty powerful concept.
Exactly, yeah. And oftentimes when people are asking me questions about like the Great Unconformity, somewhere up around Yavapai Geology Museum, and they've seen something about this unconformity of, over 1 billion years missing. And that's when I'll point out some of the supergroup layers that you can see from Yavapai Geology Museum and be like, well, yes, in some places there's over 1 billion years missing, but in other places, part of that is there. We've got part of that, and that picture you showed of the supergroup island that you can see from Yavapai Geology Museum is one of my favorite things to talk about. It's just that I don't talk about it too often with people because you have to cover a lot of ground in order to get there.
It's a little bit advanced, isn't it?
Yeah. Exactly. But I love when I get into the conversations with people and I'm able to get there. To get to the point where I'm actually able to point out that this was once an island in an ancient sea, and that there was a shoreline. There's an ancient shoreline, actually surrounding this island. That's one of my favorite things about Grand Canyon.
We've got to keep working at it. That's what this GeoFest is all about, is trying to make, bring the geosciences to the fore a little bit, the science literacy part of it. Did you know then that you've been to Mary Coulter's fireplace in Bright Angel Museum there?
Yes.
So in the 20s and the 30s, they were interpreting these islands, the Shinemu Islands, as sticking up into the Tapeats Sea. So if people want to check out what the level of interpretation in the 30s, go to the museum and you'll see that this concept of an island sticking up into the Cambrian Sea it wasn't too advanced for them. It shouldn't be that advanced for us either. So let's keep trying.
Yeah. Exactly. Yeah. And it's one of my favorite things about the Trail of Time, is that depiction of missing time. And I feel like it's something, unfortunately, that a lot of folks who are just kind of out there walking the rim and looking at the views of the canyon, as they're walking the Trail of Time, it's a more subtle aspect of it that's harder to pick up. The gaps.
Yeah.
As you're walking the trail, for those folks who might not know, as you're walking the Trail of Time, at the proper ages along the trail, you've got examples of all the different rocks in the canyon. But in between all of those examples, there's these sometimes there are little gaps. Sometimes you have like 3 rock layers, like right in a row, like the Tonto group, like boom, boom, boom. But then you'll walk for like minutes and there's no rocks. And when you're in that gap, you're in an unconformity.
Right.
And I love that about the Trail of Time.
Yeah, sort of visceral learning. You just ask somebody, "Hey, how come there's no rocks here?" Oh,
exactly. Yeah.
Okay, well that's great. And I suppose we'll have questions from people on Facebook and go from there.
Yeah. Yeah. Awesome. Thank you very much. Of course. Thank you, Dr. Karlstrom.
All right, great.
Hi. So our topic for this day of Grand Canyon Geology Festival, or GeoFest 2020, is of course unconformities, gaps in the geologic record, or missing time. And right behind me is actually a great example of the great unconformity that Dr. Karlstrom was just talking about, where Tapete Sandstone is sitting directly on Vishnu basement rocks, a gap of over 1 billion years. But before our next talk, I wanted to bring you down the South Kaibab Trail and show you one of my favorite things here in Grand Canyon. This rock. I can feel your confusion from here. Why, you ask, with so many amazing things in Grand Canyon, is this rock one of my favorites? Well, it's not so much the rock. It's actually the story that it has to tell us. You see, the first time I ever hiked down this trail, when I got to this part of it, I was looking for rocks just like this. And this is the first one that I found. And when I saw it, I was ecstatic because I knew the story that it had to tell me. You see, I'm sitting on a boulder of Tapete Sandstone, which has fallen from an outcrop up above me. But this rock is not Tapete Sandstone. This huge chunk of rock is actually a piece of Shinemu sandstone, which is part of the Grand Canyon supergroup. And it's over 500 million years older than the Tapete Sandstone. So how did it get here? How did it come to be encased in a giant chunk of Tapete Sandstone? Well, that story is going to be a big part of our next talk. But just to give you a little bit of a preview, I want you to imagine a very different landscape around me. Over 500 million years ago, this was a shallow sea. And rising up out of that shallow sea were islands of huge sheer cliffs of Shinemu sandstone, just like this. And being deposited around the shorelines of those islands were beach sands, sands which eventually became the Tapete Sandstone. And every once in a while, big chunks of that Shinemu sandstone would break off from the cliffs, come tumbling down, and land in those beach sands at the base of the cliffs. That's where this rock came from. It tells us a story about an incredibly different landscape that existed over 500 million years ago, where rocks were falling off cliffs and landing on the beach. And that is incredible to me. And our next speaker is going to be telling you a lot more about that story, which involves rapidly rising sea levels all over the world, a long period of incredible erosion, which contributed a lot to these unconformities that we've been talking about. So I hope you enjoy our next speaker and his story about these unconformities that we're talking about today.
All right, so welcome everybody. Thanks for joining us here today on this talk of our day of the Grand Canyon Geology Festival, GeoFest 2020, focusing on unconformities and missing time. Here talking with us today is Dr. James Hagedorn at the Denver Museum of Nature and Science. He's the curator of geology at the Denver Museum of Nature and Science, and we're very fortunate to have him joining us here today. Oh, that's a nice shirt. That is an awesome shirt. I've got more than a few shirts with dinosaurs on them myself. So, all right. Well, thanks for being here with us today.
Thanks for having me. Looking forward to it. Welcome, everyone.
Yeah. All right.
So the plan today is I'm going to talk to you about one of the biggest flooding events in all of Earth history. And you may have heard about this in some of these other presentations, but I mean, why go back way deep in time and study ancient rocks at the bottom of this big hole called the Grand Canyon? Like, why should you or even my neighbor care about this, right? Well, it turns out that giant flooding events that are recorded or fossilized in ancient rocks are actually relevant to today and the future, not to mention understanding how our planet operates. And so my plan is to spend 10 or 15 minutes with you today, show you some cool images, talk to you about some of the science we're doing here, both at the Denver Museum and also in the Canyon and with partners all over the West, and try to make it sound like something that's relevant and interesting, because it turns out it is. Okay, so I'm going to screen share here. Joel's going to turn off for a bit, and then he's going to join me back again, and barring any catastrophic techno difficulties, we'll talk a little bit at the end, okay? And I'm looking forward to hearing all your questions and find out what you're interested in based on some of the stuff we talk about today. So looking forward to it. So give me just a second here to get this thing turned on here. All right, here we go. All right, now you don't have to go into deep time to know where this place is, because it's the rock we live on, planet Earth. And you know, one of the beautiful things about planet Earth today is it's a blue planet, it's a brown planet, some places it's a pink planet. But it's also got a lot of white stuff on it. And on this picture here, most of the swirly white stuff that you see are clouds. But if you look down at the bottom of the diagram here where my mouse is, you see that there's a big ice cap. And in fact, this ice that we see on at the poles of our planet, and indeed in some cases in really large areas over the tops of mountain ranges, is actually an unusual feature for our planet. Because during most of Earth's history, our planet has been warmer, kind of like it's getting warmer now. And what's relevant is that when you melt all this ice that's built up on continents and other places, it turns into water and it dribbles down into the oceans. And when it does that, it floods the planet. And we're watching that happen today. Every year, the sea level of the planet raises by on the order of the thickness of maybe 1 or 2 or 3 credit cards, depending on where you are. So not by a much, but over lots of time, as this slide illustrates, that's a real challenging situation for our world, because areas that are near coasts or that are low-lying are actually starting to get flooded more and more and getting extreme weather and other impacts of that. And so, you know, one of the best ways to understand this kind of large-scale planetary flooding isn't necessarily to go flood our planet today and figure it out while we're in our scuba gear underwater at the top of the Eiffel Tower, but rather to go back into deep time when our planet has been just tremendously flooded before, and when many of the continents were blanketed by oceans, or at least shallow seas. And so this is a picture of what the Earth looked like about 500 million years ago during what's called the Cambrian period. And so one of the coolest things about the Grand Canyon is it's got some of the best rocks from this giant flooding event or transgression that occurred back in the Cambrian period. And these rocks are layered at the bottom of the Grand Canyon, and they tell the story of this global scale flooding event. And what's amazing is that even though we are still looking at these rocks that my dad always says, don't we already know everything about the Grand Canyon? That we've got new analytical tools and new processes that we can use to study these rocks and figure out what happened before, during, and after this supercontinental global scale flooding event. Sometimes it's called the Sauk transgression. So how did geologists go figure this stuff out? So we're going to go take a look at some rocks right now, because looking at rocks are fun. These are layered horizontal rocks. This is known as the Tapete sandstone. So some ancient deposits filled with sand grains laid rocks down over this big bump here. And what that bump is? It's granite. It's a rock that cools from lava underground. And it's basically a hill. This is like a fossilized hill that these sands are lapping up and going across. And what's cool about that is the flooding event is recorded right at the interface where that hill gets buried by the sand and the advancing, in this case, probably seas. Here's another example from the Grand Canyon. These are these horizontal stratified rocks. We're going to zoom in on this. Whoa, we're going to get really close. About as close as you can get during the coronavirus to the Tapete sandstone. And here is a little trough, this little schniblet of rock right here below these horizontally stratified rocks is basically like a paleo or an ancient valley or a little depression or maybe a bay. And so one of the things that we've been doing is a team of scientists have been going back to the canyon and other places like this, is we've been studying this interface between the world before this great flooding event and the world after it, right? And part of the trick of that is to figure out the clues that'll tell us what that world was like during these changes. And it turns out that in your backyard, whether you're tuning in from Jordan down here in the lower right, or you're tuning in from Colorado, here's right in my backyard, that the same process has been noted all over our planet. In fact, here's, this is not too far from our little mini Grand Canyon called the Glenwood Canyon, where we've got basically nice or sort of squished up ancient rocks that are about 1 billion years old being topped over by these horizontal stratified rocks. We call them the Sawatch sandstone here in Colorado, but they're the same as those in the bottom of the Grand Canyon. Here's an example from northern New York with a student walking along these Precambrian or sort of billion-year-old rocks that are getting just, this flood is just covering this surface. This surface is often known as the Great Unconformity. And Carl Karlstrom and Wayne Rainey have talked a little bit about that in some of these other presentations that you might be seeing online here. Here's an example from Jordan, not too far from Petra. Here's a big, basically paleo hill or paleo mountain that is then topped over by Cambrian age sandstones that are flooding the continent. Here's a little pickup truck to give you some scale. So this is not like an itty bitty flood. This is a big, honking monster event that is global in nature. And it really illustrates that going to places where these rocks are really exposed, like the Grand Canyon, has implications not only for this area, but for understanding our whole planet's history. And so here's Carl Karlstrom measuring the orientations of some of these beds that are formed as waves and dunes of sand migrate at the bottom of rivers and beaches in these horizontal layers. And we go out to the field and measure these things and try to figure out, you know, just exactly how did this happen and what kind of environments do these represent. One of the things that we want to do is we want to get a sense of, you know, if I were to fly back in time and go back in my time traveling helicopter, which by the way would be a pretty cool thing to invent. Elon Musk, get on it, will you? What would we call that, like the Tesla copter or something? Anyway, so we go back in time and we were to look down and try to get a Google Earth image of the world during the Grand Canyon. What would the Grand Canyon look like, right, at that moment in time? So here's a picture of the Grand Canyon. You can kind of see takes this shape where all these little red triangles are. These are all places where we have digitally measured the thickness of these horizontal rocks that were deposited on top of this ancient surface. And I'm going to turn this information, the thicknesses of rock that build up on a surface, actually tell you something. Because where there's a paleo valley or a paleo canyon, or maybe there's a deep bay, you can pile up more rock there. And when there's an ancient hill or an ancient island, you can't pile up as much rock on top of it. So it turns out that one of the ways to get at ancient topography or to figure out the paleo thicknesses or the paleo satellite view, if you will, of ancient Earth is to actually digitally or in person measure the thickness of rocks. And we started to do that in the Grand Canyon. And this is some brand new data on that. And I know this looks like a crazy diagram that maybe the Grateful Dead might have had on the side of their tour bus, but this is what's called an isopac map, and the different colors represent the thicknesses of rocks. And so you can think of these colors. So for example, in this case, blue are rock where these layered rocks, the Topete sandstone isn't very thick. Red are places where it is really thick. And kind of greens and everything are kind of in between. And so you could think of blue as being areas that in the past might have been highs. So right here, this might have been a paleo high. Maybe it was an island, maybe it was a hill. And maybe this area up here in the upper left was a deep basin. Maybe it was like the Grand Canyon. Maybe it was like an underwater chasm or a bay. And so these are the types of work that our team is starting to do in the canyon. And just to sort of show you a close-up view, we've got a ton of data. So all these little dots are places where we've digitally measured the thicknesses of these rocks, and we're just now starting to try to figure out, what does this tell us? You know, was the Grand Canyon a bunch of bumpy surfaces like the Black Hills today, or was it as flat as a pancake? Well, it certainly doesn't look flat as a pancake. But to kind of take this the next step, we need to know what kind of sediments are filling these depressions and lapping up onto these surfaces. Are these sediments that were formed in ancient aquatic settings that were like a giant lake, or were they river systems that were filling this area up with sediments? Was it at the bottom of the ocean? And so to do that, we've got to go out and look at the rocks and the structures in them. And so this is an area that you can actually see from right near Phantom Ranch, actually, or excuse me, from the main viewpoint that overlooks Phantom Ranch. This is Utah Flats, and you can see this bowl-shaped depression here that back in this valley here is actually filled with these sediments that lapped up onto the surface. And what's amazing is if you look at these sediments, they have clues in them that tell you what environments filled these ancient landscapes. In this case, Zechariah here is standing on these huge giant crossbeds that only form in one setting today and in one setting in the past. These are giant sand dunes, perhaps produced in a coastal dune field. There are even little structures on here that tell you the wind direction. These are called adhesion structures or low amplitude ripples. And on some of these surfaces, there are actually little tracks and trails of little kind of cockroach-like critters that might have cruised up and down the dunes. And so what's great about this is that in this case, in this particular setting, we know what the ancient environments were that were being deposited on to that great unconformity surface. We can even tell where there were little streams and rivers by the cross-bedding that we've got our hand on right here, and other little clues in the rock. In some cases, in this case, Zechariah is pointing that over to his left, that actually the currents were flowing that way. So we can even not only tell you what environments were there, but we can go back to rocks 500 million years ago and tell you when the wind was blowing and what direction it was going in, or whether there were streams going by. We can even find evidence of ancient groundwater, that is the water table below the surface. No geologic dowsing rod required. So here's Zechariah's toe pointing at a bunch of these weird little bumpy things that form right at the interface of that ancient water table below this dune field. And so we've taken together some of this data, and lots of other geologists have collected this data over the year, and we've tried to compile it together and integrate it together with an understanding of how this place changed over time. And we're trying to produce diagrams like this that'll help both the public and scientists come up with hypotheses or educated views, if you will, of what this ancient landscape looked like as it was being flooded and as it was being filled. There were clearly high points like these. There were maybe low points with streams and dunes in them. There was probably an ocean out there, maybe some barrier islands. But hey, stay tuned. Check in with our next lecture when we present some data from our work that we just got funded on by the National Science Foundation. So hopefully in 3 more years, we'll know a little bit more and be able to present it to you today. But one of the exciting things that we're realizing is that not only can we recognize what these ancient landscapes might have looked like and what kind of sediments filled them, but it turns out that there were probably honking earthquakes and faults moving around that actual landscape at the time. And here's a crew of students here standing next to what is essentially a giant debris flow, or basically a rock avalanche that came downhill. And this is in those same boring horizontal stratified layered rocks. And so that tells us that maybe this landscape was a little bit more active than we thought it was. And in fact, when you look at these rocks from a distance, you look at this slide right here and you say, oh, great, it's all pretty much horizontal. We'll measure the thickness, call it a sandstone, and move on. Well, geologists over the years have noticed funny things in those, and we're scaffolding on their work to kind of figure this out a little bit more detail. And here's some mapping that a number of people have done over the years, Mike Timmons and Carl Kostrom and others. Here's some people for scale, I know. In the Grand Canyon, people are generally very small on all pictures. But it turns out that some of these rocks aren't completely horizontal. They're kind of been turned up. They've been twisted upward by mountain building or faults and then planed off at the top by these other horizontal rocks. And in fact, there's even fossilized debris flows or rock avalanches preserved in the rock record that tells us that maybe the Grand Canyon was not only a place with hills and valleys and islands and chasms, but also with some pretty cool, active, tectonic activity or faults happening. And we're looking forward to trying to piece together this picture in the coming years. And who knows, maybe one of you can help us. So with that in mind, I'm going to stop here and stop sharing my screen. And Joel or other folks, if you got any questions or want to talk about it, I'm all ears. I'm here to help.
All right. Well, awesome. Thank you so much for that. I mean, I find it fascinating just how much we can learn by looking at things like well, I'm a sedimentologist myself, and that's why I'm a sedimentologist. I mean, you hear people talk about, you know, volcanoes and what's going on, you know, like down in the mantle, and all of that stuff is fascinating. But I love what is happening up here on the surface of the planet. You know, where we live, things we can actually see and things we look at, and being able to visualize ancient landscapes in such detail. You know, to imagine ancient rivers and mountains and, you know, that nothing ever saw that once existed on the planet just blows me away. And that's why
it's like we're detectives in deep time, right? And instead of, you know, DNA and a fingerprint and like a hair cell, you know, hair and a, you know, something or other, or a footprint in the mud, we've got ripples or big debris flows that are now a giant jumble of conglomeratic rock, or maybe we've got some crystals or a fossil that tell us an age or an environment. And, you know, the study of sedimentary rocks, I mean, Andy Knoll, I think, said this maybe 20 years ago, and he said, you know, we are the custodians of Earth history, right? Because fundamentally, the tree ring record, if you will, or the pages of the book of deep time are recorded mostly in sedimentary rocks that are laid down layer by layer. And they've been beat up, they've been cooked, they've been squashed, they've been ripped apart. In some places like the Grand Canyon, they're still mostly there and they have a lot of great data still in them. But our job is to go to those rocks and pull out the clues in them to decipher, like, what did that crime scene look like 500 million years ago in this case? Or what events were happening in that world, right? Like, what is my paleo Google satellite, what's my paleo Google Earth image, right?
Yeah. Yeah.
And that's a hypothesis, right?
Yeah. And I mean, and a detective coming like upon a crime scene, that's an analogy I've used myself, you know, many times. You know, everything's happened up to this point, and we're coming on the scene and we're trying to piece together the clues and the evidence and okay, what was the sequence of events? What happened when? How did things get to look like the way they are now? A lot of what you were talking about, like mentioning, you know, the processes that we're seeing that were happening in the Grand Canyon region, you know, the same sorts of processes that are happening all over the world, and the same sorts of processes that are generally happening today. Another concept I love talking about is that kind of core principle in geology of that the present is the key to the past, and that, you know, we look around at what's happening on our planet today and we use all of those processes that we're seeing occurring in real time and say, okay, how can we use that to explain what we're seeing in the ancient past?
Yeah. And you know what's great is we're standing on the shoulders of giants. I mean, so many amazing geologists have worked in the Grand Canyon, but, you know, I have an iPhone, right? And Mark Schmitz has a mass spec that can zap a zircon and date it with 10 times the precision that, you know, probably our predecessors could. And so, you know, the Grand Canyon is a fantastic natural laboratory to resolve these issues. And, you know, I've looked at these horizontal rocks that are in the Grand Canyon called the Tapete Sandstone. I've looked at them on every continent except Antarctica. I don't like cold that much, so I'm not going. But, you know, the answers from the Grand Canyon that our team and other scientists are helping to come out aren't just going to answer questions about the Grand Canyon. They're going to answer questions about rocks on other planets, you know, on other continents that tell us about our planet as a whole, right? And in some ways, as those rocks inform us about the Grand Canyon. And, you know, the beauty is, you know, we have the internet, we're Zooming with one another right now, but, you know, I can get a paper from an author in China in 2 nanoseconds and from someone in Austria the next day, right? Whereas if you think about it, a geologist working 100 years ago in the Grand Canyon had to, you know, write a letter out and maybe know who to write to get information about rocks that were analogous, or maybe that had geologically been like, they're rocks that are like the Grand Canyon, but they're stuck over in Australia now because the continent's ripped apart. Yep. How would you know to call someone you couldn't call someone. How would you know to write a letter that went on a ship that went over to Australia to talk about those rocks and get information that would help you interpret your rocks in the Grand Canyon. Today, we do that all at an instant. And so we have some great advantages. We're doing this now, which and we're scaffolding on the work of our predecessors. And so to me, that's one of the exciting reasons to go back to places like the Grand Canyon and drill into these, not literally drill, but, dig into these, incredibly well-preserved rocks to understand things about our whole planet. And, at the beginning, I showed you that our planet's flooding right now, right? It's not flooding maybe as fast as it did back in the day, or maybe it is, we don't know. But I don't really want to run the flooding experiment in my lifetime or my kids' lifetime. I'd rather go back and study a rock and figure out what's happening and what can we do about it. A lot better that way.
Yeah, and that's also a point I make to folks a lot, that this isn't just some kind of abstract concept that we're studying out of pure curiosity. It has applications to the world we're living in today. Studying these events and these processes in the past tells us, how our planet got to be how it is now, and helps us maybe predict what it's going to look like in the future. And with climate change, I mean, boy, yeah, that's vital. That's vital information, so definitely worth studying. And the Tapeats, of course, you're talking a lot about the Tapeats sandstone. That is my favorite rock layer in the canyon. A lot of people ask me, what's your favorite rock?
I love it.
Yeah.
Well, hey, when the pandemic ends, let's all go hang out on the Tapeats together and think about what the world looked like when the Tapeats was being deposited. But in the meantime, I'm going to go, and there's lots of other great talks in this series, and I hope you all enjoy them. And thank you so much for having me, Joel. This is super fun. Love geologizing remotely, and looking forward to do it in person again soon.
Absolutely. Yeah. Well, thank you very much for being with us here today.
All right. Take care.
Right.
See ya.
Bye.
So we've been talking here today about unconformities, gaps in the geologic record, or missing time. And I decided to wrap things up by coming down here to a spot along the South Kaibab Trail called Skeleton Point. Because from here, we've got a great view of all three sets of those rocks that we were talking about yesterday. The basement rocks down there at the bottom of the canyon, the supergroup layers there in the middle, although of course not all of them, and the layered Paleozoic rocks up on top. From here, we've also got a great view of the Colorado River way down there at the bottom, and just to the right of it, Phantom Ranch. And from this spot, I can actually hear that river. Now, as we've been talking about, there are unconformities or gaps in the record between a lot of the different rocks we see here. Some of those unconformities are over 1 billion years of missing time. Now, unconformities, as we've been talking about, are erosion surfaces formed during times when sediments weren't being deposited or rocks were even actively being eroded by rivers like that one. Rivers and streams and wind eroding rocks and transporting them, sometimes over great distances, to redeposit them. So how do we get at what happened during those gaps, those periods of missing time in the geologic record? What rocks used to be there, if any? How were they eroded? Where were they transported to? How did geologists answer these questions? Well, our next talk is about a fairly new and very powerful method that geologists are increasingly using to answer questions like those. It's a technique that I'm using in my own thesis research, and I'm citing about 6 papers written by our next speaker.
Well, hello everybody, and welcome to our final talk here for today of the first day of Grand Canyon Geology Festival, or GeoFest 2020. And we're here today with Dr. George Garrels, who's going to be talking to us about, giving us a little bit of an introduction about how we tell time when we're studying the rocks of Grand Canyon, which is something we're going to be talking a lot more about here later in the week. Now, Dr. Garrels grew up in Tucson, Arizona. He spent a lot of time hiking around the mountains and canyons of Arizona. And after he completed his undergraduate degree at the University of Arizona in Tucson, he went off to graduate school at the University of Southern California and Caltech, and was fortunate enough then to be able to come back to the University of Arizona as a faculty member. And his research is focused on 3 different aspects of geochronology, which The first of which is the development of new techniques for determining ages of rocks and minerals. This involves fiddling around with mass spectrometers, which are really cool, super cool instruments that can measure isotope ratios on tiny, tiny amounts of material. It's the ratio of those parent and daughter isotopes that we use to determine ages of rocks. Second is the application of those methods to studying history of many different regions around of the world. And third is opening up their lab to researchers and students from other universities who use those instruments and their expertise to date samples. Hosting hundreds of scientists for each year, working on samples from all over the world and all throughout geologic time. So thank you, Dr. Garrels, for being with us here today.
Well, thank you very much. Let me go ahead and share my screen. We'll pull up the PowerPoint here. Thank you for the opportunity to participate in this wonderful Grand Canyon GeoFest. My talk today is going to focus on the origin of the sedimentary layers that create the spectacular scenery that people come to appreciate in the Grand Canyon. These sedimentary layers are interpreted traditionally to be a result primarily of changes in sea level. Times of high sea level are recorded by limestone. Times of low sea level are recorded by the clastic sediments that are shed from nearby or local source areas into the area that is now the Grand Canyon. There's no doubt that the first part of this story is correct. If you see here some limestone on the right, clearly this sedimentary material accumulated on the floor of shallow marine seaways that existed during various times of the Paleozoic. This would be in the Muav Formation, the red wall limestone, and then the Kaibab Formation at the top. Our work during the past 15 years suggests that the clastic sediments that make up much of the Grand Canyon stratigraphy record an amazing history of where that sediment was generated and transported. The traditional view is that sediments like sandstone, siltstone, mudstone, and shale, shown here just with an example of a sandstone, consist of minerals or rock fragments that were derived from pre-existing rocks exposed in nearby or local source areas. By looking at the ages of detrital zircon grains, which we can also extract from these sedimentary layers, we're able to confirm the traditional view that the sediments low in the Grand Canyon sequence here, Tapeats, Bright Angel, that sediment looks like it was indeed derived from local source rocks, maybe local areas. For example, Vishnu schist probably was exposed locally in Cambrian time, being eroded and weathered, sediment coming off of those highland areas and being deposited here as the Tapeats and Bright Angel formations. But the ages of zircons in younger sediments from the Temple Butte Formation all the way to the very top of the Grand Canyon layers are not a great match for local sources. And instead, they indicate that much of this sediment was actually shed from the Appalachian Mountains, not from local source areas, but far distant source areas, maybe thousands of miles from northern Arizona at various times during the Paleozoic. And these zircon grains, together with the sand and the mud and the silt that you see here, all of that sedimentary material was transported from the Appalachians across North America and ended up here in northern Arizona in the Grand Canyon sequence. And this is the incredible journey that I talk about in the title of my talk here. It's the transport of this sedimentary material from the Appalachian source regions across the continent into the Grand Canyon. So in the next couple of slides, let me tell you a little bit about how we do these kinds of analyses. I've had lots of collaborators that have helped us with this project, collecting the samples. And then most of the analyses shown here with these names of undergraduate students who conducted the analyses and did much of the interpretation. So here we go, our 5 steps of doing this kind of analysis. The first thing, which all geologists love to do, is going off to the field and collecting samples. This sampling was done with undergraduate students. These are freshmen in my oceanography class back in 2006. As part of the Trail of Time project, we were able to go down into the Grand Canyon and collect samples from each of the different sedimentary layers. We then took those samples back to our laboratory, and you can see we're manually crushing that material. And out of that crushed material, then we can extract out the zircon crystals that we're going to use to determine the ages and talk about where the sediment came from. What's amazing about doing this is that these zircons are tiny. If you were to have these crystals on a sheet of paper in front of you, you might be able to see tiny little brown dots. These are less than a millimeter, about 1/3 of a millimeter in length or smaller. We then take those zircon crystals and we put them into our mass spectrometer. This is a laser ablation mass spectrometer, feeding samples into the mass spectrometer here. The laser excavates a pit down into the surface of the zircon crystal. That laser diameter is about the diameter of a hair, about 20 microns in diameter. We drill down about 10 microns, so a very, very tiny volume of material is excavated. We then measure the uranium and lead isotopes that come out of that ablated material. That's done with the mass spectrometer, which is tuned to measure isotopes of uranium and lead. By the ratio of uranium to lead and the decay constant, we can calculate the age of that crystal. And so that's what Justin here. Justin is actually a linguistics major who was part of this project. He learned a lot about earth science as part of running our mass spectrometer, helping us do these analyses. And this is the end product of that lab work. Shown across the x-axis here, these are the ages of those detrital zircon crystals from the present day 0 back to 1 billion years ago, 2 billion years ago, 3 billion years ago. And then shown on the vertical axis here, the height of these bars just represents the abundance of different ages. So for example, Tapeats formation, we analyzed 200 different crystals, and you can see that most of the ages are between 1.8 and 1.6, between 1.5 and 1.4. So then what we want to do is we want to take the ages that we measure from these samples, and we want to compare those ages with the ages of known rocks in North America, and thereby we can figure out where that sediment may have been generated and transported from. And so here's step 4. What we want to do is come up with this compilation. This is a compilation from many, many different research projects characterizing the ages of rocks in North America. Here's the Grand Canyon. You can see we're in the green bar, 1.8 to 1.7. So it looks like the traditional view is correct. Looks like Tapeats has a lot of this locally derived igneous material from source rocks nearby. A little bit of the light green, a little bit of the 1.4s here, but most of that sediment looks like it comes from southwestern part of North America. So what we can do is we can kind of characterize the ages of rocks in southwestern North America and use that as a fingerprint for the ages of zircons that we would expect to have come from this area. And that's what the curve on the bottom here does. This is like our fingerprint for southwestern North America. Any sediment coming from this area should have lots of ages in this range, lots of ages in this range. But as I mentioned, our interpretation is that a lot of sediment came from the Appalachian Mountains. If that's the case, then the zircon ages should look something like this. This is a fingerprint for the Appalachian origin. Lots of 1.2 to 1.0, 600 MA, and then 500 to 300 MA zircons. That's what characterizes the Appalachians. If Grand Canyon strata have a lot of Appalachian-derived material, we should see lots of ages in these ranges of the green. So it's a very simple system. It's just matching the patterns of our samples that are unknowns compared with these fingerprints from the known areas, the reference areas, the source areas. And then comes the fun part. This is the last part. This is the interpretive aspect of doing this kind of work. We use these wonderful maps that Ron Blakey has put together. These are paleogeographic views of what the community thinks that North America looked like back through time. So here's the Grand Canyon. This is Arizona. This is Greenland up here. So this is all of the North American continent. This would be during late Paleozoic time. Here are the Appalachian Mountains forming as North America collides with South America, Africa, Eurasia. This is when Pangaea is first beginning to form. And so what we show as our interpretations in green are the lines of rivers that we think may have transported sediment during this time. In yellow are the wind directions of the trade winds. Here's the paleo-equator during that time. And so sediment would have been transported in the direction of the yellow areas by the wind during this time. So we take advantage of these great reconstructions of Ron Blakey's to say something about the provenance or the transport history of that sedimentary material. Okay, let's jump in and do this. You can help me. You now know enough about detrital zircon methodology that you can do this. These are the ages that we have from the Tapeats and the Bright Angel. Lots of 1816, lots of 14s. I think the interpretation very strongly supports the traditional view that a lot of the sediment in these Cambrian, the lower layers of the Grand Canyon here, the Tapeats and the Bright Angel, those are coming from nearby source areas that were high during Cambrian time, probably just like the Vishnu. The Vishnu has exactly these same ages, so probably local basement rock being the source for sediments in those units. So here's the paleogeographic view of what we think was going on. This is North America, a big island by itself during Cambrian time. Here's Grand Canyon, Hudson's Bay, Greenland to get you oriented. Transcontinental Arch was a high area in the middle of the continent during this time. And the green shows what we think are the river systems that are transporting sediment off of the Transcontinental Arch out into the Grand Canyon. And this is exactly what the original stratigraphers of the Grand Canyon geology suggested, local derivation of this sediment in the Cambrian. Well, the story gets more interesting here when you get a little bit higher in the sequence. So this is the Muav Cambrian. Right above that is the Temple Butte, which you know is late Devonian in age. It occurs right below the Red Wall of Mississippian. And what we see in the Temple Butte, looks like we've analyzed about 300 zircon grains. Looks like a lot of local derivation, right? A lot of 1/8s, a lot of 1/4s, a little more of the 1.0 to 1.2. The best area that you can get these grains from is actually the purple area of eastern North America. This is called the Grenville origin, and we think that's the source for these grains. And then look at this, the youngest grains down here on the left side between 600 and 400 MA. You just can't find a source for zircons of those ages out here in the western part of North America, even the central part of North America. Really, the best place that you can find, you can point to for ages of that range is in the Appalachian origin. And so this is our interpretation from Ron Blakey's view. This is a complicated reconstruction. Here's North America, Grand Canyon. Here's when North America was just beginning to become part of Pangaea. The European Baltica cratons have collided with North America, forming the Caledonides. Small microcontinents out in the Paleo-Atlantic have collided with North America, forming the original earliest phase of the Appalachian Mountains. We call this the Acadian Mountain Belt. We know that the Acadian Mountain Belt has lots of zircons that are 600 to 400 MA. They are the perfect source, really the only source that you could call on to get zircons of the ages that we see in the Temple Butte. So this is a complicated history. Somehow river systems were able to tap into the headlands here in this mountain system, carry that sediment somehow across the central part of North American continent, and carry that sediment all the way out here to the Grand Canyon area. It's possible there was some trade wind transport. These are the arrows showing the trade winds. Here's the Paleo Equator north of the Grand Canyon during Devonian time. And so it could be that there was also some Aeolian wind transport of that sediment. But most likely, our first time when we see big transcontinental rivers carrying sediment. Next layer up, as you know, is the Red Wall, Mississippian age. This is a time when sea level was high, at least relative to northern Arizona. So Arizona was covered by the shallow marine seaway. There's not a lot of zircons in limestone, and so we don't have any age information that we can use to say something about sediment transport. The sediment was probably forming on the ocean floor with not a lot of input from other areas during Mississippian Red Wall time. But the story that's really interesting here in the Mississippi, and this is the Surprise Canyon Formation, the first layer above the Red Wall limestone. And look at this, it's got conglomerate in it. That would tell you, boy, there must have been some mountainous areas, some topography, some high topography not too far away to contribute all this coarse material into the Mississippian units of the Grand Canyon out here. Well, let's look at the zircon ages from Surprise Canyon Formation. Looks like we've analyzed 380 of them. Yeah, there are a few that look like they came from local sources, but look at this. Look at this big blast of zircons, 1.2 to 1.0. Really, the only place that those zircons could have come from is this purple belt here, the Grenville origin. And then lots of 600, 700, 400, 500 MA grains. Really, the only place you can get those is in the Appalachian origin during this time period in the late Mississippian. So that's our interpretation, is that during late Mississippian time in the Surprise Canyon Formation, the Appalachians are really forming. They're a big mountain range during this time. This is when South America, Africa, Europe, Baltica, they're all colliding with North America. This is when Pangaea is just starting to come together. Those mountain systems must have been super high. They may have been Himalayan height. Maybe you need that kind of a mountain range to get conglomerate coming all the way from the eastern side of North America, coming all the way across the North American central part of the continent and ending up out here in the Grand Canyon area. This is a mystery. This is a puzzle. How do we get conglomerate coming all the way from the Appalachians out to the Surprise Canyon Formation? The story continues to be really interesting in the Supai, and maybe even becomes a little more interesting. You know, the Supai is a complicated sequence of sandstones, siltstones, mudstones, and shales kind of interleaved, reflecting a very dynamic environment during Pennsylvanian time. Let's look at what the zircons tell us about the source. Yes, there is certainly some local sediment in the Supai Formation, but there's a lot of this Grenville age material, and then it continues to be a lot of the sediment again coming from the Appalachians during this time period. So kind of a continuation of the Surprise Canyon Formation. Here, not the conglomerates, but here this interlayered sequence of sands and muds and silts and shales. So that sequence has a really interesting history. If you look at the map of the Pennsylvanian time, the Supai is out here forming during this time. It's a very complicated dispersal pattern of river systems and maybe the trade winds carrying sediment from the Appalachians. This is the last stage of Appalachian Mountain Formation, somehow carrying the sediment across these other basins and carrying that sediment all the way out here to the Supai Formation in the Grand Canyon sequence. This was really complicated in the Southwest. These are the ancestral Rocky Mountains that we know were high during this time. And so somehow we have to imagine this incredible journey of sediment coming through the ancestral Rockies or around the ancestral, maybe over the top of this. Somehow the sediment is coming, bypassing the ancestral Rockies, dominating the sediment budget that we see here in the Surprise Canyon Formation, or in the Supai, even though we know these ancestral Rocky Mountains uplifts were high during this time. So it must have been a combination of transcontinental rivers and the trade winds bringing sediment into the area during this time. Well, let's talk a little bit about the origin of this layering. It's kind of a second order feature that you see on here. We think that the layering within the Supai actually reflects global processes that were operating during Pennsylvanian time. So here's North America. This is all Pangaea, right? The big supercontinent that existed in Pennsylvanian time. Here are the Appalachian Mountains, Toledanides, Hercynian mountain ranges. So sediment was coming off of here into the Grand Canyon area during this time. But during this time, we know that there was a big ice sheet capping the southern south pole of the Earth, the southern hemisphere. And just like today, that ice sheet gets broader, gets smaller, it expands and contracts as climate changes. As that happens, sea level goes up and down, and that changes the patterns of erosion and sediment dispersal and sediment accumulation seen out here in the Supai. And so this complicated pattern, we think, is a kind of a modulating, a second order effect of these complicated paleoclimate changes that were taking place during the Pennsylvanian time. So when you look at this part of the Grand Canyon stratigraphy, you need to think about tectonics, forming mountain ranges, forming supercontinents, changing sea level, and that's what produces this amazingly complicated record out in the Grand Canyon. And then during Permian time, you know, the layers at the very top here would be the Hermit, the Coconino, the Toroweap, and then the Kaibab. We've analyzed zircons from all those different sediments. Let's see where that sediment came from. Yeah, there's some older, maybe locally derived material, but most of the sediment, maybe 60+% of that sediment, was coming from the eastern part of North America, the Grenville mountain system. And then look at this nearly continuous distribution of ages from about 700 MA to about 300 MA. This record of ages is actually a great reflection of what we see in the Appalachian Mountains. If you look at the ages of igneous rocks in the Appalachians, it's actually a very, very similar record to what we see here. I would actually make the case that if you want to study the Appalachian Mountains, maybe one of the best places in the world that you can go to is right here in the Grand Canyon, because this is where the sediment came from that was being eroded off of the Appalachian Mountains. The rocks of those ages in the Appalachian Mountains have largely been removed. And this is the sedimentary archive of what existed in the Appalachian Mountains during Permian time. So this is a great record of the Appalachian Mountains. This is the record of the Pangaea supercontinent being assembled, preserved in these sedimentary rocks of the Grand Canyon. Here's the paleogeographic view of what North America looked like during this time. River systems carrying sediment off of the Appalachian mountain systems, referred to as the Alleghanian, orogeny, the Ouachita mountain systems, somehow getting that sediment through or around or over the top or across the ancestral Rockies and ending up out here in the Grand Canyon area. Probably much of that was a big erg deposit like the Sahara Desert is today, dune system in the Coconino sandstones. But the origin of that sediment was a long ways away, several thousand miles away, originating in these mountain systems. And so I'll leave you with this conclusion. When you look at the amazingly scenic and beautiful stratigraphy of the Grand Canyon, think about this amazing, incredible journey of sediment coming from in the lower parts of the sequence here, from local sedimentary, local mountain ranges in these local sediments, and then all the way up through the sequence here, most of the Grand Canyon stratigraphy dominated by what was taking place in the eastern part of North America as the Appalachian Mountains were forming due to the assembly of Pangaea. And in the Supai Formation, this kind of paleoclimate controls sea level going up and down because of this glacial climatic change controlling the detailed patterns of stratigraphy in the middle part of the sequence here. So the Grand Canyon sequence is beautifully scenic, but it's also a fascinating record of how Pangaea was assembled and how changes in paleoclimate have affected the stratigraphy in this part of North America. So I think I'll stop there and see if Joel has some questions, and we can have some conversation about what zircons tell us about the history of the Grand Canyon. You need to unmute.
There we go. Yeah, thank you so much for for talking to us about that, because again, it's a subject that I'm fascinated by as someone who's actually doing some detrital zircon work as part of my thesis research, and I can attest to how much work it is to collect those samples and tease those tiny little zircon crystals out of those rocks. It takes a lot of time and a lot of work and a lot of patience. But the stories that we get out of those tiny little crystals never cease to amaze me. The fact that you can actually get at stories about the formation of rivers and transport of sediment across continents and the movement of continents and the assembly and breakup of supercontinents and the uplift and erosion of mountain ranges. You can get at all of that by just not just, but big part of it by looking at these tiny little crystals and getting information about ages from them. It really amazes me.
Well, and that's one of the things that we see commonly in earth science these days is that nanotechnology, being able to make observations on a really small scale, or mega technology, satellite images of the earth, that looking at things in different scales of space and in time, provides just amazing insights into how these processes operate. I think it was mentioned to Joel that if you added up all of the zircon material I've ever analyzed in my career, and you put it into a pile on a piece of paper, it's so small you wouldn't even be able to see it. It's insignificant, the amount of material that we analyze, and yet the information that you get, I think, is telling us really amazing things about, in this case, the Grand Canyon. We have a similar record from the layers that sit on top of the plateau here, the Mesozoic sediments that sit on top. We also have ages from those, and it tells us an amazing history of sediment transport, again, coming from the Appalachians and other areas. And then this has been done now in other places around the world. And so it's the application of these new technologies that allows us to say new and exciting things about how the Earth works.
Yeah, absolutely. And there was actually one question it did occur to me about this mystery you mentioned regarding the Surprise Canyon formation, which again, that's this purple stuff right behind me here. How you transport conglomerate across a continent. And I was wondering if, in dating the Surprise Canyon formation, if folks tried to, if you tried to get zircon specifically from clasts within the conglomerate, as opposed to the matrix, surrounding clasts, and whether there was any difference between them, whether you learned anything about it by looking at that.
Yeah, that's a great question. You could imagine that maybe the coarser pebbles in the Surprise Canyon were coming from a local source area, giving you the older 1.8 and 1.4 age zircons. And then the finer sedimentary material, maybe that was the part that was transported thousands of miles from somewhere else. So we actually wanted to test that possibility when we were collecting our samples. And so of our, I think, 5 samples from the Surprise Canyon formation, 2 of them consisted only of the cobbles, the pebbles. We chipped out just those individual pebbles. We put those together and we processed those. And then we collected 3 of our samples that were just from the sedimentary matrix, the fine sand and silt matrix around those little cobbles. And what would you guess were the results of those cobbles versus the matrix? What's your prediction?
Well, I'll tell you, I have conglomerate in my field areas for my thesis research, and I tried to do the same thing. And the information I got from clasts was confusing, to say the least. I did not know what to make of it. So my prediction, based on the fact that you said that it is kind of a mystery of where this stuff came from, is that the clasts probably also had Appalachian zircons in them.
You got it. Indistinguishable. You look at the age distributions from the cobbles, the little pebbles, and you look at the age distribution from the fine-grained matrix, they are indistinguishable.
Wow.
And so I think exactly your question is right on. I'm glad that we did that separation in advance, because otherwise that would be a great answer to the problem. The pebbles are coming from somewhere different, but that can't be the case.
Right.
Somehow you have to be able to get those pebbles from the same area that you're getting that fine-grained matrix material. And I would love to have other collaborators come in, maybe experts who know more about the Surprise Canyon Formation, or Joel, your work, maybe we can tease out an answer to this problem. I think it's an amazing mystery.
Yeah, definitely. And that's one awesome thing about, well, science in general, but about geology, is that there's always these mysteries. There's always more to learn. Even about some places as studied as the Grand Canyon has been, there's still things we don't know and don't understand, and trying to figure out. So,
yeah, I guess I would just add in terms of collaborators, that this is a game that really anyone can play these days. You don't have to be a geochronologist and spend your whole career in the lab. This is something that really any student can do. Come to our lab or come to other labs in the US that do this kind of work. It doesn't take a lot of training. Within the same day that you arrive, you'll be zapping zircons. It's kind of like a video game, shooting the laser and hitting the zircons. And 15 seconds later, you get the age. And it's like, oh, this amazing age that you get tells you something new about how that sedimentary unit formed. And so this is something that we do a lot of, is have students come into the lab. Undergraduate students, K through 12. We've had middle school students come in and do science fair projects. This is the kind of work that really anyone can do in terms of generating the ages and then interpreting the ages. It's a little more complicated, but it's still a pretty simple issue of just matching patterns. The zircon ages look the same as one place and not the same as somewhere else. That tells you something really important about where that sedimentary material came from. So I would invite anyone who's interested to get involved in doing these kinds of analyses from Grand Canyon stratigraphy. Obviously, you need to work carefully with the Park Service people to do this kind of work, and we've had a great collaboration with them, and part of the Trail of Time. It's been a great collaboration, but definitely find a way to get involved in this, and let's answer some more of these problems from the Grand Canyon.
Yeah. All right. Well, thanks again so much for being with us here today, Dr. Garrels, and for talking with us.
Thank you very much for the opportunity.
Yeah. Of course.
Well, that's about it for today's talks about unconformities and missing time. And to wrap things up today, I brought you all out to one of the most incredible viewpoints in the entire Grand Canyon. It's a place called Plateau Point. It's a side hike from Indian Garden along the Bright Angel Trail, and from out here at Plateau Point at the edge of the Tonto Plateau, down within Grand Canyon, we are looking straight down into the inner gorge to the Colorado River below. There's some rapids down there. Straight across the way, of course, these incredible outcrops of Grand Canyon supergroup that we've been talking about here today and yesterday as well. And in the distance there as well, the great unconformity where Tapeats Sandstone, which is what I'm standing on, is sitting directly on the Vishnu basement rocks. So I hope yesterday's talks about rocks, today's talks about unconformities have given you a better understanding of the geology of Grand Canyon. Now, tomorrow, we're going to actually have a special day tomorrow, National Fossil Day. So tomorrow is going to be all about paleontology, all about incredible fossils that we find here in Grand Canyon. So I hope you all come and check that out tomorrow. Till then, have a good night, everybody. Thanks for being here for the virtual GeoFest at Grand Canyon National Park.